For this lecture, I decided that we should go somewhere else. So where shall we go? Well, for a graph theorist, there is really only one place in the world where you want to go: Kaliningrad. So Kaliningrad is this place in Europe that now is part of Russia. And in Kaliningrad city, there is a construction of bridges that was much more interesting 300 years ago. So you have this small island where now only two bridges remain. Not very interesting, much more interesting in the times of Leonhard Euler. So Leonhard Euler was a Swiss mathematician who at some point was in Kaliningrad. And in that day and age, the city looked a bit different. So first of all, the name of the city was not Kaliningrad, it was Königsberg, but that's not very important. The important thing is that it looked like this. So just look at the upper part of the picture. So here you can see that you have the island in the middle of the city where the cathedral is. You have the southern bank of the river, the northern bank of the river, and you have an eastern peninsula here. And you also have bridges, so notice that you had this bridge here, you have this bridge here, you have this bridge here, and this bridge here. Then you have a bridge to the eastern part, a bridge from the eastern part to the northern part, and a bridge across here. What Euler was wondering is, can I start from a point, any point in Königsberg, and walk along these bridges, crossing each bridge exactly once, and coming back to the place where I started? This is a question that Euler asked in 1735, and this picture and the facing page is from his manuscript from that year, where he solved this problem in greater generality. And in some sense, this was what gave birth to the science of graph theory. So Euler concluded that no, it is not possible. Wherever you start, you will not be able to go back to that point, going through all bridges exactly once. You have to cross at least one bridge at least twice to do that. And he started wondering, why is that possible? What feature would have been needed to make this possible? And what in general? How do I solve this? Well, the way to look at this problem to make it mathematical, which Euler explains in great detail in his paper that if you know Latin, I recommend you read, and if you don't, I recommend you learn Latin and read, is the following: that if you forget about the general geographic components of the city and look at it from what we now call a pure graph theoretic point of view. So each region, the island, the banks, and the eastern part, you realize them as vertices, and each bridge is an edge. Now you're asking, in this graph, can I start in one point and pass each edge exactly once, coming back to this same point? And formulated in this way, you quickly realize that there is nothing special with Königsberg. You can ask this problem about just about any graph. So let's look at this. So in honor of Leonhard Euler, we call the graph Eulerian if this is possible. So an Eulerian or an Euler graph is a graph where there is a closed trail that includes all edges in G. So remember, trail means that edges don't repeat. So you don't cross any edge more than once. Including all edges means that you cross each edge at least once, so exactly once. And closed means that the end point is equal to the starting point. So such a graph where you could realize Euler's dream in Königsberg is called an Eulerian graph. And if you manage to write down such a trail, then that trail is called an Euler trail. the other way to say this, or another way to say this, is that in an Euler trail, you take a pencil and you follow all the edges of the graph exactly once without lifting a pencil. A more violent way is you walk around in a city. After you cross each bridge, you blow it up, and the point is you should be able to come back to where you started. Obviously, you cannot use the bridges you have already blown up. A slightly different notion of that is a graph that is semi-Eulerian. So semi-Eulerian means that you start in a vertex, you go through all edges exactly once, and you end in a different vertex. So the trail is not closed, but still it includes all edges in your graph G. So the question that Euler asked, and that I ask you now, is there a precise condition or precise conditions that tell you exactly when this is possible? If I give you a huge graph with thousands of vertices, it will take you forever to try to find such a trail. But maybe there's a way to quickly see if this is possible or not. Before we go through Euler's solution to this problem, I want to ask you to try yourself. So let's look at the graph that we got from Königsberg, and that looked like this. And I told you that there was no way of finding an Euler trail in this graph. So try yourself, and as you fail to find this path, which you will because it's impossible, not because you're bad, try to figure out what the problem is. And then try other graphs. Is it possible with the cycle graph? Is it possible with, I don't know, draw some random graphs somewhere and check if you can or cannot find an Euler trail, and try maybe to get some idea of what the problem seems to be. This is the question that Euler asked in his 1735 paper. And in a section of this paper, he summarizes his findings. And notice the words that appear are impar and par. So impar means odd and par means even. And indeed, the theorem that now carries Euler's name is the following. A connected graph is Eulerian if and only if each vertex has even degree. Of course, Euler didn't have the language to express this, so he expressed himself differently, but he proves precisely this. A connected graph has the property that you can go through all edges exactly once and come back to the same point, precisely when each vertex has even degree. So you check the degree of each vertex. If it is even, you're good. If you have a vertex with odd degree, you're not. So before proving this theorem, let's go back and look at Königsberg. So here you can see that, in fact, this vertex has degree 3, this has degree 5, this has degree 3, and this has degree 3. So not only is this graph not Eulerian, but it's really the worst possible thing that can happen. All vertices have odd degree.